work yesterday. Having issues on a problem, how to solve it. I was like, where's the video? Because I had my notes open yet.
Oh, but I sent it out, right?
Yeah, you did.
Yeah.
I pondered over that problem for an hour.
It happens sometimes. So guys, let's see. Today we're going to cover 7.3. So let me open this up here. And I'm going to open this up in OneNote so that we can this. Yeah, OneNote. We're skipping 7.2. Yeah, we are skipping section 7.2. So give me 1 second, y'all. I'm going to tell you guys in 1 quick second. Un momento, por favor. Let's see, is this us? Yes, this is what we were the other day. Yeah, this is what we were. Okay, so let's come back. Where is it? Over here. Let's print this out. And let me open up this guy and print it. And yes. Oh, let's see. Okay, it should be here. Let me scroll all the way down to the bottom. Aha. There we go. All right, so yeah, y'all, we are skipping 7.2. We're going directly into 7.3. So give me 1 second to make sure that you guys can see what's happening. Yes, look if you can. So you were all asking, what was 7.2? 7.2 is actually graphing polar equations. Just a kind of like a quick idea of when we first learned how to graph, y'all. And I'm just going to kind of do this briefly because I do want us to go on to 7.3, but I'm going to kind of make this up. So let's go, let me see if I have some more room over. Okay, so whenever you first learned how to graph, whatever it was, whenever you were in 8th grade or 9th grade or 10th grade, whatever it happened to be, for the most part, the way we learned how to graph, and I'm just going to make this up. Suppose I'm going to ask you to graph, I don't know, y equals 3x, right? For the most part, the way we learned how to graph was we would make a little table. And we would say, we're going to pick some numbers for x, like we're going to pick -1, and we're going to pick 0, and we're going to pick 2. And we're going to plug in those numbers and figure out what we're going to get for y. Right? So you would do this and you would say, well, look, what's 3 times -1? -3. What's 3 times 0? And 3 times 2? Okay. And then you'd come back over here, x and y, and we would say -1, 1, 2, 3. That would be this point here. 0, 0 would be there. 1, 2, 4, 5, 6. And we would have, a line that would look something like that. Right? That's for the most part. Whenever we first learned how to graph, that's how we all did it, right? We didn't automatically learn y equals mx plus b or anything like that. We always learned by plotting coordinates. You do the same thing in polar coordinates. The thing about polar coordinates, it takes a really long time to do those graphs. And we have graphing calculators now, and for the most part, that's how you're going to do those graphs, okay? So it's not actually part of the curriculum. It's an optional section. I just opted not to cover it because it's very time consuming and it's very tedious. But you can do this using a calculator. But what isn't optional is 7.3. So, but roughly this is how you would do. You would graph polar equations all the same way. You'd have to make a table of values. And just like, when you're doing a line, obviously a line, you only need 2 points to graph a line, but we always did 3 as a check. With polar coordinates, you got to plot a whole bunch of points, okay? So anywho, let me come back over here and let's go through 7.3, and we are going to talk about complex numbers in polar form. And I just want to make sure that I am recording the session, but yes, we are. Okay, just double check it. Okay, so complex numbers in polar form, 7.3. We're going to talk about how do we plot complex numbers in the complex plane. So a complex number a plus bi has two parts, the real part a and the imaginary part b. So two axes are required to represent a plus bi graphically. Okay, so guys, before we actually start about, talk about how to plot points or complex numbers, do y'all remember what imaginary numbers are? Yeah, so let's go through just what's an imaginary number. Okay. So let me ask you a question. Simple question. What's the square root of 4? Okay. Now my question to you is why? Why is it 2? Because 2 times 2 is 4, right? But I've asked you, what's the square root of negative 4? What would you say? It's going to be 2i, right? Because that's right. We can rewrite this, y'all, as the square root of 4 times the square root of negative 1, where I is the square root of negative 1. We already know the square root of 4 is 2. The square root of negative 1 is I. So we end up with 2i, right? So in the real numbers, we can take the square root of numbers as long as the number that we're taking the square root of is positive or 0. When we start trying to take the square root of negative numbers, that's when we get into this imaginary business, okay? And so what we're going to be doing is we're going to be talking about how can we graph these complex numbers on the complex plane. So let's come back over here. So again, that's just kind of a rough idea or a rough, refresher, I guess, in what imaginary numbers are. Okay. So it says two axes are required to represent a plus bi graphically. So we have the real axis. This is kind of like our x-axis, and the horizontal axis, and then the imaginary axis is going to be the vertical, kind of like the y-axis. Okay. And it says the real and imaginary axis together form the complex plane. So the complex number z is equal to a plus bi can be written as an ordered pair, ab, and then we would graph it like this, okay? So look, we're going to do the same thing for these three problems. It says graph the complex numbers in the complex plane. So remember, y'all, I'm going to think of each of these numbers as an a plus bi. So if we were to do this, y'all agree with me that a would be negative 1 and b would be negative 5? Okay, so then the way we're going to do this is we're going to graph it like that. Negative 1 and, negative 5. So if I'm going to plot the point negative 1 minus 5i, I'm going to go 1 to the left, and then 1, 2, 3, 4, 5 down. And here would be negative 1 minus 5i. All right, let's try the next one. So again, I'm thinking about these numbers in complex form, a plus bi. So what would you guys, if the number I have is just a 3i, what would you say the a would be equal to? 0, very good. What about my b? 3. So then it's kind of like I'm plotting the point 0 and 3. So if we were going to plot the point 0 and 3, we would just go from the middle, we just go up 3, 1, 2, 3, and then this would be the point 3i. And so the same thing, I'm going to do it right here, a plus bi, right? And so what would you say my a is in this case if all I have is negative 4? What would you say a is? Negative 4. And what about b? 0. There you go. So this is the point that we're going to plot. Negative 4 is 0, which means we're going to go 1, 2, 3, 4 right here. And that's our point, negative 4. Okay. So graphing complex numbers in the complex plane, pretty straightforward, just like your plotting points, right? Because that's pretty much what we're doing. And the next thing we're going to talk about, y'all, is something called the absolute value of a complex number. So the absolute value of a complex number is actually what we refer to as the distance between that point AB and 0, 0 in the complex plane. So we're measuring this distance right here, y'all, okay? And we have a formula for it. So one of the terms we use for the absolute value, we call it the modulus or the magnitude. Okay, this means the length. And the formula we have right here, y'all, says the absolute value of z, or the magnitude of z, is equal to the square root of a squared plus b squared. All right, so first thing I'm going to do in my problem, y'all, I'm going to think about this in the form a plus bi. So I know that my a is -7 and my b happens to be -12. And so when we're going to find the magnitude of z, we're going to say this is the square root of -7 squared plus -12 squared. And let's see, -7 when I square it, 49. 12 when I square it, 144. And I want to say that 49 plus 144 should be something like 193 square root, right? John, am I okay? We're good? It's exactly what it means. The square root, the absolute value of z is equal to the square root of 193. And I'm just going to leave it like that because 193 is not a number that I can simplify, so I'll leave it that way. So let's try to do the same thing for number 5. So guys, in number 5, if I think about this in the form a plus bi, a is the number 4 and b is a -6. So I'm looking at the absolute value of z. It's going to be 4 squared plus -6 squared. So 4 squared is 16. -6 when we square it gives me a 36. And 16 and 36 should be something like 52. But I bet you we can break down the square root of 52. So if I take 52, y'all, and I just start dividing it by 2, that's going to give me 2 and 26. And if I break 26 down, that's going to give me 2 and 13, right? Remember what the square root means? The square root means I'm getting pairs. What number do we have a pair of? So the 2 comes outside, and the 13 stays indoors, and we found the magnitude of z, or the length of z, right? So in the next couple of sections, we're going to be talking about vectors, and vector is like a directed line segment. And in doing that, sometimes we need to know the length of those vectors for certain applications. All right. So let me get a little sip of water here, y'all, and then we'll keep going. Okay, so the next one here says, how do we write the polar form of a complex number? So it says the complex number z equals a plus bi is said to be in rectangular or Cartesian form because a and b are the coordinates of the point a and b in any rectangular coordinate system formed by the complex plane. So the polar form, the way we can write this in polar or trigonometric form of a complex number, z equals a plus bi, is z is equal to r cosine theta plus I sine theta, where a is r cosine theta, b equals r sine theta, r is the square root of a squared plus b squared, and the tangent of theta is equal to b divided by a, as long as a is 0. Well, because it's sort of the same idea. It's just complex numbers, they're always written in the form a plus bi. So you're talking about continuity in college algebra, that's how we write complex numbers, always in the form a plus bi. So there is still some continuity there. Yeah. Okay, so it says the value of r is the modulus of z, remember the distance, and we can say that theta is what we call the argument of z, okay? There are infinitely many choices for theta, but normally theta is taken on the interval from 0 to 2 pi or from 0 to 360 degrees. So John, the other day you were asking about how do you know if the number of the angle is written in degrees or radians? So again, when it's written in degrees, it'll have those little degree symbols, right? If it doesn't, it's understood to be in radians. Okay, so sometimes the way we write this, y'all, r cosine theta, I sine theta, sometimes they write it like this. Z equals R CIS. So the C obviously stands for cosine, I is our imaginary number, the S is for sine. Okay, so like cosine, I sine, right? That sometimes they write it that way. I usually stick with the cosine and the sine, but if you write the CIS, that's fine. And it says, additionally, for any real number theta, we have something called Euler's formula, which says that e to the power I theta is cosine theta plus I sine theta, but I don't think we have any of these problems in our homework. So we'll hold off on that part there. Okay, so let's take a look here, y'all. We're going to see if we can figure out how to do some of these problems. It says, write the complex number in polar form. Okay, so the first thing we're going to do, y'all, is let me kind of zoom out just a little bit so I can see everything on my screen. The first thing I want to do, I want to see if I can find my R, okay? Because remember, I'm going to be writing these numbers so they look like this. Z equals R, and then cosine theta plus I sine theta. So the first thing I'm going to do, I'm going to see if I can find my R. So R is equal to the square root of, look what we have, a squared plus b squared. So do y'all agree with me that a is the negative square root of 2 over 2? And b is also the negative square root of 2 over 2? Just by looking at my picture. And so what we're going to do, we're going to come back over here. We're going to say, look, negative square root of 2 over 2 squared plus another negative square root of 2 over 2 squared. Okay. And so let's see. So number one, they're both negative inside, but because we square them, they're going to become positive, right? So do y'all agree that the square and the square root are going to cancel each other out? Yeah, so we're going to end up with 2 over, what's 2 squared on the bottom of? There you go. Plus another 2 over 4. Okay. So 2 over 4 plus another 2 over 4 is 4 over 4. And 4 divided by 4 is 1. And what's the square root of 1? Anybody know? Square root of 1? Oh, don't make it that hard. What times what gives you 1? There you go. Okay, so we know that R is equal to 1. Okay. Now, second thing we need to find, y'all, we need to find our angle. So I'm going to zoom out a little bit over here. Let me see, here we go. And I'm going to look at this part up here, y'all, where it says the tangent of theta is equal to b over a. Okay, I have that all the way there at the top. So we know what our b and a are. Our b and a are both the negative square root of 2 over 2. So this is telling me that the tangent of theta is equal to the negative square root of 2 over 2 divided by another negative square root of 2 over 2. This is telling me that the tangent of theta is equal to 1, right? So what I need to figure out is, when is the tangent equal to 1? So y'all, what I'm going to do, I'm going to come back up here, and I'm going to come back to my document. I'm going to come all the way back to the top. Let me get my sheet right here. This is the one that I want. And I'm going to open this up for us. Here we go. Okay, so when is the tangent of theta equal to 1? Any other time? 225, right? So I come up with two answers, 45 or 225, right? So guys, look, when I come back over here, I'm going to ask you a question. Very good. Since they're both negative, we're going to be in quadrant 3, right? So if we're in quadrant 3, shouldn't we be using the 225? Very good. So we're going to say now that our angle is 225 degrees, okay? And so, guys, we're going to write our answer in complex form, okay? So notice how we write it. In complex form, we're going to say z equals r cosine theta plus I sine theta. So we're going to say z equals, what did we get for r? Anybody remember what we got for r? 1. Cosine of 25, oops, plus I sine 225. And I'm going to go like this so that we know we're talking about this. So y'all, having that little cheat sheet that has all the angles and my 6 trig functions, right? This one right here, this is going to come in super helpful because not only is the tangent of theta equal to 1 at 45 degrees, but it's also at 225. And I have to look at my A and B so I can figure out what quadrant I'm in. So since A and B were both negative, we knew we were going to be in quadrant 3, right? All right, let's see if we can do the same thing for number 7. We're going to do this problem exactly the same way. So I'm going to kind of zoom over here, y'all. And first question I want to ask you, do you know what our A and B are here? Yeah, there you go. So A is 12, B is 5, right? Remember, guys, we're going to find the R by saying we're going to take the square root of 12 squared plus 5 squared. Okay. So let's see, 12 squared is going to give me 144. 5 squared is 25. Anybody know what's 144 and 25? 169. Anybody know what's this? 13. Look at that. Boom. R is 13. Okay, so we got R being 13. We have this part. Now remember, y'all, the second part is we know that the tangent of our angle is equal to B over A. So this is telling me that the tangent of my angle is going to be equal to 5 over 12. So if I want to find my angle theta, 2 things we can do. One thing is we can come back and we can use our chart. Here's my tangent, right? Do I ever have a 5 over 12 in my tangent column? No. Okay, so if I can't use that, then I'm going to have to go inverse tangent. Okay, so theta is going to be the inverse tangent, y'all, of 5 over 12. So first thing I'm going to do, I'm going to pull up my calculator, and I'm going to turn it on, let me clear it. I'm just going to check to see what mode I'm in. I'm in radian mode, but I'm going to go ahead and move it over to degrees, just because that's what I like dealing with. All right, so we're going to go second tangent inverse. Oops, that's not. Second tangent inverse, okay, of 5 over 12 and 22.6. There you go. So theta is 22.6 degrees. Okay. And so now we can go ahead and write our answer. And it's going to say z equals, here's the basic formula, y'all. R cosine theta plus I sine theta. So we're going to say z equals what, 13? And then, y'all, if you want to use that little abbreviation, you can put CIS and then 22.6 degrees. You can write it like that if you want to. If it's easier for you, if you like the way it looks, writing it like this. Yeah. No, it's the imaginary eye. And we figured it out. Okay. Yeah, but in your homework, they're going to ask you to go ahead and approximate to like 1 decimal point or something like that. 22.6.
So we can decide to cos I times 22.6.
So look, let's do this. Let's go, what's 13, right? Times the cosine of 22.6. All right, what number do you think we should be coming up with? What is my A? 12. Take a look. Pretty close? Pretty close, right? And then if we take 13 times the sine of 22.6, we should get 5, right? 22.6, something like that. We should get something really close to 5. 4.995. That's pretty close, right? Yeah, it should, and it should give you, I mean, it should give you options, you know what I mean? But if you put the CIS, you should be okay. Yeah. All right, good questions, y'all. Very good questions. Okay, let's take a look at number 8. Number 8 says, let's write z equals 6 cosine of 135 plus I sine of 135 in a rectangular form, a plus bi. Okay, we're just going to use the calculator for this, right? So a couple ways you can do it. You can definitely use the calculator. Just to give you a heads up, 135, don't we have it here already? Yeah, so remember, cosine is going to be what? Negative square root of 2 over 2, and sine is positive square root of 2 over 2? Okay, so I'm looking at 135, y'all. The cosine is the negative square root of 2 over 2, and the sine is the positive square root of 2 over 2, right? So I'm going to go like this. Look, z equals 6. We said cosine was the negative square root of 2 over 2. We said sine was the positive square root of 2 over 2. So when we multiply by 6, aren't these 2's going to cancel with that 6 and make it into a what? Into a 3, because the 2's are on the bottom, so the 2 is dividing into the 6. So wouldn't I end up with a negative 3 square root of 2 plus I 3 square root of 2? Did I make any sense there how I did that part? Are we good? Right, because 2 goes into 6 3 times, right? Both those 2's are going to divide into that 6. So look, guys, if I actually write it out, I'll write it like this. So 6 with a negative square root of 2 over 2 plus I 6 square root of 2 over 2. But then these 2's cancel with those 6's to give us our 3's, right? All right, good deal, good deal. Excellent. All right, so the second part we have over here, y'all, is how do we multiply or divide complex numbers in polar form? Okay. Yeah, go ahead. Yeah, go ahead. So the way we're going to multiply complex numbers, y'all, so take a look right here. We're going to call this first complex number Z1, and the formula is like Z1 equals R1 cosine theta 1 plus I sine theta 1, right? Because why the 1? Because it's the first complex number, right? And then the second number, Z2, is going to be R2 cosine theta 2 plus I sine theta 2. So it's real straightforward, y'all. Look at the formula. If we're going to multiply the two numbers together, we take the R1 and the R2, we multiply those numbers together. We take our angles theta 1 and theta 2, and we add them together, right? Straightforward, easy breezy cover girl, should work out nice and pretty. Okay, so let's take a look here. It says, given Z1 is 20 cosine 30 degrees plus I sine 30 degrees, and Z2 is 3 cosine 210 and I sine 210, look what we're doing. We're going to multiply those two numbers together. So we're going to say Z1 times Z2 is equal to. First thing I need to do, I need to take my R1 and my R2 and multiply those numbers together. So look, here's my R1 and here's my R2. What's 20 times 3? 60. Boom. Times the cosine of and the sine of we got to take these angles, y'all, and add them together. So 30 and 210 should be 240. Okay. And at that point, y'all, we're good to go. You can stop right here. It's just telling me write the product in polar form. We are in polar form, okay? So again, all we're doing, multiplying the two r's together and our angles, all we got to do, Adam and Eve, right? All right, let's try number 10. We're going to go about it exactly the same way. So look at number 10. Number 10 wants me to find the quotient. So remember what the quotient means. Quotient means we're actually going to divide. So Z1 divided by Z2. I want you to take a look here. Look what we're going to do with our R values. We're going to divide them out. We're going to take R1 and we're going to divide it by R2. So what's 8 divided by 2? Good. And then for the next part, y'all, we're going to go cosine of some angle plus I sine of some angle. Okay, let's take a look at what we're going to do with our angles. Since we're dividing, we got to subtract our angles, okay? So what I'm going to do over here on the side, y'all, 7 pi over 12 minus pi over 4. What do you think my common denominator is going to be here? We're going to multiply them both by 3. Very good. So 7 pi over 12 minus 3 pi over 12 is going to give us 4 pi over 12. We can reduce it back to pi over 3, right? So then right here, y'all, we're just going to put pi over 3. Now, you guys know my fondness for degrees, right? Degrees, I just find it like super easy for you to go. Guys, if the problem starts off with radians, go ahead and write your answer in radians, okay? I'm not like opposed to working with radians. It's just that when I do problems, I find it easier to do them in degrees. But again, like when you get to this step, I mean, it's not like we were doing anything really complicated, but when you get to this step, go ahead and write it in radians because that's what we have. Okay? All right. So let's take a look at number 11. So number 11 says, given Z1 is 1/2 plus the square root of 3 over 2i, and Z2 is the square root of 3 over 2 plus 1/2 I, find Z1 times Z2 and write the answer in polar form. Okay, so first thing I would recommend that we do, y'all, let's take our Z1 and Z2 and let's convert those from rectangular form back into polar form, okay? So for Z1, y'all agree with me that A is 1/2 and B is the square root of 3 over 2? So first thing I'm going to do, y'all, I'm going to find my R1. So remember the way we find our R1. We're going to take 1/2 squared plus the square root of 3 over 2 squared, right? Okay. And we're going to go slow motion, right? So 1 squared is 1, 2 squared is 4, square root of 3 squared is just 3 over 2 squared is 4. So 1/4 plus 3/4 is 4/4. Y'all remember what, oops, what am I writing it on to? Okay. Y'all remember what the square root of 1 was? 1. Okay, boom. So we found our R1, okay? We're going to find our angle now. So remember, the way we're going to find our theta 1 is this is equal to the tan inverse of B over A, right? So theta 1 is going to be the tangent inverse of B, which is the square root of 3 over 2 divided by A, which was 1/2. So theta 1 is the tangent inverse of, remember how we divide fractions? Then we multiply by the reciprocal. So what's going to happen to that 2 on the bottom and the 2 on the top? Right here, y'all. Anybody know? But remember, we're multiplying them, so what's going to happen with those 2's? Won't they just cancel out? Yeah, there you go. So very good. Tangent, or theta 1, is tangent inverse of the square root of 3. First off, let me ask you a question. What quadrant am I in? If our number is 1/2 in the first quadrant. Okay, so guys, I'm going to pull up my chart here. Here's my tangent. Do you see the square root of 3 in my quadrant 1 for tangent? Under here, do you see a square root of 3 anywhere in there? 60 degrees, boom. Okay, so we come back over here. So we know that our theta 1 is 60 degrees. Boom, we got it. Okay. All right. We're going to do, so now guys, so look, let's write it like this. Wouldn't we say that Z1, if I write this now in polar form, wouldn't this be 1 times the cosine of 60 degrees plus I times sine of 60 degrees? I'm sorry? Yeah, you can write that. It's one of the abbreviations. Yeah, it's okay. Look, so here's my Z1, right? We wrote it in polar form. Y'all, we're going to do exactly the same thing for Z2, okay? So look, we're going to go like this. Here is my Z2. I'm just going to do it over here on the side, y'all, where I have a little bit more room. So Z2 was the square root of 3 over 2 plus 1/2 with an I. So do y'all agree with me here that A is the square root of 3 over 2 and B is 1/2? Okay, so let's see if we can find our R2. Aren't we going to take the square root of 3 over 2 and we're going to square it, and then we're going to take 1/2 and we're going to square that too? Are we going to come up with the same thing? Because all we did is we just switched those 2 around, didn't we? So we should still come up with 3 over 4 plus 1 over 4. So R2 is the square root of 4 over 4, which is the square root of 1. So very good. John says R2 is really the same thing as 1, right? Okay, let's do the same thing for our tangent, or for our theta, y'all. So remember, theta is the tangent inverse of B divided by A. So let's write it like this. Tangent inverse, B is 1/2 divided by the square root of 3 over 2. Okay. And remember, how do we divide fractions? We multiply by the reciprocal. Okay. And so theta 2, these 2's are going to cancel, is going to be, got my little inverse symbol, 1 over the square root of 3. But guys, we can rationalize that denominator. Remember when we used to do that? We would run like this. And so we'd say this is going to be the square root of 3 over 3. There's my theta 2. And so the first thing I'm going to do, y'all agree with me, we're still in quadrant 1 because of this part right here? Okay, so look, I'm going to pull up my tangent one. Do you see the square root of 3 over 3 anywhere under my tangent in the first quadrant? Under tangent, do you see square root of 3 over 3? Pi over 6 or 30 degrees, right? And the only reason I'm going to use 30 is because we use 60 the other time. You know what I mean? Good, good. All right, so theta 2 we said was what, 30 degrees? Okay, so look, y'all, I'm going to zoom out a little bit more, and I know I'm kind of running out of room here, but we'll fix it in a second. So we know that our Z2 is 1 cosine of 30 plus I sine 30, okay? So here's my Z1 that we found earlier. Here's our Z2 that we found right now. And I know I'm really, really zoomed out, so I'm going to zoom back in so we can figure out what was it we were looking for. We were trying to find Z1 times Z2. Okay, so let's see if we can do that now. So I'll tell you what I'm going to do, y'all. I'm just going to write Z1 on top of it, one cos. Okay, so it's the same thing except with 60s, right? Okay, so now, if we want to find Z1 times Z2, do you remember what we do with our radiuses? Multiply 1 times 1? Still 1. Okay, and y'all, I'm going to use John's notation, the CIS. What do we do with the angles? Do you remember? Add them together, so 30 and 60. Boom. And there's one. That was a lot of work. But let me ask you a question. Was it hard to do? Not really, right? It's not too hard. But yes, guys, sometimes they do take a little bit of time to do. It's definitely much easier when they're already given to us in polar form and all we got to do is multiply them or all we got to do is divide them, right? Yeah. Yeah. You know, part of me kind of wonders, like, you know, I finished, y'all, when I got my master's degree, I graduated in December of 1998. So I don't even know if any of you were here yet or not. But anyway, that's when I finished school. And, you know, I mean, we had graphing calculators back then too, but I mean, like we had it, there was like a TI, it's called the TI 85. I still have it. It's not that great. But anyway, but my point is, like John said, you know, there's computers that do a lot of this stuff. So I'm always kind of curious as how much of this is actually really pertinent now, because the computer will do some of this for you. But it's, you know, I guess it's always good to understand some of the basics. Yeah. Yeah.
I know the concept of car, I want to take my car that's all the engine station, it's got to replace the spot, not because all the engine station, I got to replace the spot because this is places, you know what I mean? Too much stuff to design out.
Yeah. Yeah. I know what you mean. All right. So guys, let's kind of keep moving along here and let's take a look. And it says, we're going to do some computations. We're going to compute powers of complex numbers. Okay, it's called the Moore's theorem. So it says if z equals r cosine theta plus I sine theta and n is a positive integer, then the power zn is going to be equal to, and we have it over here. So I'm going to look at the more like simplified version, y'all, right here. It's r to the n times cosine n theta plus I sine n theta. Okay, so first thing I'm going to do here, when I look at my problem, I know that my r is equal to 2, and we know that our theta is 3 pi over 16, and it looks like our n in this case is 4 because we're raising it to the 4th power. So we're going to say z to the 4th is equal to, first thing I'm going to do, take 2 to the 4th power, and then cosine of n, which is 4, times my theta, which is 3 pi over 16, plus I sine 4 times 3 pi over 16. Okay. And now I'm just going to start doing the computations. So first thing, 2 to the 4th power. Remember what 2 to the 4th power means? 2 times 2 times 2 times 2, right? So 2 times 2 is 4 times 2? 8 times 2 again? There you go. Okay. Now, let me ask you a question. Y'all agree that this 4 and that 16 will reduce to become a 4? And this 4 and that 16 will reduce to become a 4? So guys, if I use John's notation CIS, wouldn't I just have 3 pi over 4? Okay, let me, that's sort of the idea, right? So the abbreviation, so just kind of give you a heads up, last night, y'all, I was in one of my college algebra classes, and we were doing a problem, and it was ended up being something like this, like x squared is equal to 5, so we took the square root on both sides, and we wrote x equals plus or minus the square root of 5. And I asked the class, how many answers did I end up with here? Anybody know how many answers are there? 2, right? One of them is the positive square root of 5, one of them is the negative square root of 5, right? But because we write it like plus or minus, they think, oh, it's one answer, but it isn't, right? It's actually, you can actually think about this as x equals the positive square root of 5 and x equals the negative square root of 5. So like John says, it's a good idea to write out the cosine of your angle plus I sine of the angle, and then write your abbreviation so that you understand you really have the two parts, right? All right, let's take a look at number 13. So let me ask you a question, y'all. If I'm going to do 13, what do you think should be my approach? So is this number 1, is this number written in rectangular form or in polar form? It's in rectangular form, right? Do you see how easy it was for us to do number 12 because it was already in polar form? That's what we want to do here. So let's take a look. Y'all agree that my A is 2 square root of 3 and that my B is going to be equal to 2? So first thing we're going to do, y'all, we're going to find our R. So remember, the way we find this is we're going to take 2 square roots of 3 squared plus 2 squared. Okay. Question. Does anybody know what is 2 times the square root of 3 when you square it? Very good. 4 times 3. And 2 squared is just 4. So 4 times 3 is 12. 12 plus 4 is 16. And the square root of 16 is 4. Okay. Now, we need to find our angle. So remember, y'all, the way we find our angles, we're going to take the inverse tangent of 2 divided by 2 square roots of 3. Okay. So those 2's are going to cancel. I can think about this as 1 over the square root of 3. Excuse me. But remember, 1 over the square root of 3, if I rationalize my denominator, y'all, is going to be very good. It's going to be the square root of 3 over 3. Okay, so again, I'm going to come back and use my chart. First question, though. What quadrant are we in? If we're looking at 2 square root of 3 plus 2i, what quadrant are we in? 1 or 2 or 3? Okay. We're in quadrant 1. Okay, so here's my tangent. In quadrant 1, when tangent is equal to the square root of 3 over 3, we're at 30 degrees, right? Okay. So we're going to say our theta is 30 degrees. Okay, we got this one. Now, let's go ahead and write our answer in complex form, or in polar form, I'm sorry. So we're going to say z equals r, which is 4, times the cosine of 30 degrees plus I sine 30 degrees, right? And we're going to be raising this to what power, y'all? 6. Okay. So if we're going to raise this thing to the 6th power, the first thing we're going to do is we're going to take 4 to the 6th power, and then we're going to take cosine of 6 times 30 degrees plus I sine 6 times 30 degrees again. First thing I'm going to do, y'all, I'm going to actually use my calculator here. I want to figure out what's 4 to the power 6. That'll be a pretty big number. 4 to the power 6 is 4,096, right? Excuse me. And then 6 times 30? Anybody know? 180, there you go. Guys, can we write it like this? Using our little abbreviations. And we got it. Well, I'm glad it does, man. I'm glad it does. Guys, we're almost finished with the problem. I thought we were finished. We're not. Look, what does it say? So now we got to reverse it. Not a big deal. Look, what are we looking at? We're looking at the cosine of 180 and we're looking at the sine of 180, right? Here's my chart. Where's 180? Right here. Here's the cosine. Here's the sine. So the cosine is what, -1? The sine is 0. So we're going to go like this. Z to the 6 is 4,096. Remember, we're going to write like this. We said the cosine was what number again? Cosine was, let me zoom out so you can see it. -1, sine was 0, right? Okay, so look, cosine is -1 plus sine is 0. So look what I'm doing, y'all. I'm just going to distribute this. 4,096 times a -1. What would it be? What's 4,096? Yeah, negative 4,096. And 4,096 times 0i is just 0. There's our answer. There it is in rectangular form. All right, let me ask you another question. When we had our number from the get-go, was our number in rectangular or was it in polar form? It was in rectangular, right? What did we do? We converted it to polar, and then once we did that, what did we do after the end? We went back to rectangular, right? Sometimes people say, why don't we just try to deal with it in rectangular to begin with? Because I want to show you all something. Remember what our number was? It was like 2 square root of 3 plus 2i raised to the power 6. You know what that would mean, right? Wouldn't that mean that we'd have to do this? That's not going to look pretty. You know what I mean? It's going to look really, really, really messy trying to do that 6 times. You know what I mean? You could try it. See, I don't know if I don't know, like my calculator is an 83 plus, it's a little bit older. Maybe it'll do it, maybe it won't. I'm not certain. But my point is, we would have to do this thing here, y'all, 6 times, and that's going to be a really big pain. It give you an answer after all? There you go. You got it. So, yeah, so converting it to polar, guys, even though there is some work there, it's not really all that difficult, okay? It's steps, right? It's steps. Okay, we're almost done here, y'all. We just got a little bit more to do. And so it says, find the nth roots of a complex number. Okay, so remember, y'all, when we're doing roots, like we understand what a square root means, right? And let me ask y'all a quick question. That looks really messy. Do y'all know what the cubic root of 8 is? Or do you understand? Do you know what the cubic root means?
No.
Okay. So a little while ago, when I asked you, like, what's the square root of 49? We did it, I think, with 4 or something like that. But you said this would be what? Well, if it's just a square root, it's just +7. The only time we're going to use plus or minus, y'all, is if there's a plus or minus in front. This is what we call the principal square root. And if I were to ask you why, you would say, well, 7 times 7 is what? 49, right? How many 7s do we have? But no, I'll circle them for you. How many 7s are there? There's 2 of them, right? This is why it's called the square root. You're getting pairs. So when it's the cube root, I'm getting what? I'm not getting pairs, but I'm getting triples, right? Sets of 3. What 2 numbers do you know multiply to 8? Any 2 numbers besides 1 and 8? 2 and 4. Can you break down 4 into? Okay. What number do we have 3 of? That's what we call that the cubic root. Does that make sense? That's the idea, y'all. So remember when you were a kid, maybe you did this when you were a kid. There's change on the counter. Maybe it's grandpa's change, maybe it's dad's change, whatever. And you're going to your room and you kind of do that number, and you get to your room and you put all the change, right? You got a piggy bank. And whether it's pennies or quarters, say it was quarters. Don't you do this with the quarters? 1, 2, 3, 4. 1, 2, 3, 4, right? You're grouping in terms of 4, right? If you got nickels, sometimes you go like 1, 2, 3, 4, 5, right? You might get 5, or you might try to get 10, whatever it is, right? But you're grouping them together. When you have the square root or the cube root or the fourth root or the 13th root, you're grouping in terms of that number. You're trying to get sets of 13 or sets of 3 or whatever it happens to be. I'm sorry? Then you just leave it as it is. Like we did earlier, I think we got like 193, the square root of 193 of those 8. We left it as the square root of 193, right? If we can't break it down, we don't. But if we can, then we tried it, okay? So let's come back over here and let's take a look at what we're looking at. We're looking at nth roots, right? So this could be square roots, cube roots, fourth roots, fifth roots, so on and so forth. So it says if z equals r cosine theta, I sine theta, then for any integer n is greater than or equal to 2, so we got to be at least be looking at square roots or more, then z has what we call distinct or n distinct nth roots of the form. And there's a formula right here. So look, let's take a look. It says wk is equal to the nth root of r times cosine of. So y'all, the first one here, this is when my angles are in radians. This is when my angles are in degrees. We're going to take theta plus 2 pi k over n, or we're going to take theta plus 360k over n, okay? Where k is equal to 0, 1, 2, all the way to n minus 1. So I'm going to explain the idea to you guys in our first problem here. Well, so let's take a look at this one here. It says, yeah, find the fourth roots of 81. Okay, so the first thing I'm going to do, y'all, I'm going to think of this number in rectangular form. I'm looking for the fourth roots of 81. So do y'all agree with me that my A is equal to 81 and my B is equal to 0? Okay. First thing I'm going to do, y'all, I want to write this number in complex form. Okay, so first thing we're going to do to write it in complex form, we're going to find our R. Remember, it's the square root of A squared plus B squared. So R is going to be equal to the square root of 81 squared plus 0 squared. Not R squared, but just R. So R is equal to the square root of 81 squared. So isn't it just 81? Okay. And let's see, we need to see if we can find our angle theta. So remember what we said theta is equal to. Theta is the tangent inverse, y'all, of B divided by A. So we know that B is 0. So 0 divided by 81 is still 0. Okay. So y'all, I'm going to pull up my chart again. Here it is. I'm sorry. But it's 81 squared, right? Okay, so y'all, when I pull up my angle, what angle are we looking at? When is the tangent equal to 0? At 0 degrees, right? Okay, so my theta here, y'all, is 0 degrees, okay? All right, so now that we have that, let's see if we can write our answer in polar form. So I'm going to say z equals 81, and then we're going to go CIS, 0 degrees, right? Well, so we're actually, so if you think about it this way, if A is 81 and B is 0, I'm going to scroll all the way back up to the top where we started today. Remember who we started today? If we were going to plot, I'm going to write it over here, my fourth complex number, which is just 81, wouldn't it be all the way over there? So I'm not in the quadrant, I'm actually on the horizontal axis, right?
So,
That's why, so 0 degrees is not actually in the quadrant, but because the point is on 81, wouldn't that point be all the way over here? So that's why we know we're at 0 degrees and not pi. Does that make sense? Good question, very good question.
so anything that's on
It's not in the quadrant, right? Because the quadrants are the 4 little pieces, not the boundaries themselves. Okay, so let's look, y'all. We're going to write the 4th roots of 81. So I want you to notice the notation they use here. They go WK, where K is going to be 0, 1, 2, all the way to N minus 1. So in this case, y'all, since we're looking for the 4th roots, N is going to be equal to 4. So if N is equal to 4, do y'all agree with me that N minus 1 would be equal to 3? So look, we're going to write it like this. W. We're going to go from 0 all the way to 3. So K is going to have these values, y'all. Okay. The first one I'm going to do is when K equals 0. So we're going to have the 4th root of 81, and we're going to go ahead and do this in degrees. Cosine of theta, which we said was 0, plus 360 times K, which is 0 as well, all over N, which is 4, plus I sine, same thing. 0 plus 360 times 0 all over 4. Okay, 4th root of 81, y'all, is 3, right? Just to kind of give you a rough explanation again, y'all, why is the 4th root of 81 3? Remember what we said before. If I'm looking at the 4th root of 81, I'm going to be grouping in terms of 4, right? I don't know about you all, but when I think of 81, I think of 9 times 9, and each of those 9s breaks up into what? 3 and 3. How many 3s do we have? There we go. Right? So let me scroll back over here, okay? And let's see if we can't figure this thing out. So let's see. CIS 0? Okay. All right. Usually, y'all, it's going to ask us to actually write these numbers out, okay? So instead of me writing it like this, let's do it this way. Let's do this. Let's try something. So I'm going to write it like this. Let's see, cosine. So we already know that our theta is 0, so I don't really need to worry about that part. What's 360 divided by 4? 90 times 0 plus I 90 times 0, okay, which is going to be equal to, let's see, cosine of 0 plus I sine of 0 is going to be equal to, I'm going to pull up my chart here, y'all. Cosine of 0 is 1. Sine of 0 is 0. So this is going to be 3 times 1 plus 0i. This is just going to be equal to 3. Okay. Now, we did this for 0. We're going to do this now, y'all, for 1. Okay. So I want to show you something. Remember, we had already simplified because our angle theta was 0, and we took 4 into 360 both times. We're really coming up with like a 90, and this value here, y'all, is going to be my k. So look, I'm going to write it like this. Cosine of 90, now I'm letting k be equal to 1. So if k is equal to 1, then that's a 1 plus I sine 90 times 1 itself, not an I, I'll mark it a 1. okay? So look, we're going to go slow again here. Cosine, okay, let's see. Cosine of 90, I'm going to pull up my chart again, y'all. Cosine of 90 is 0. Sine of 90 is 1. Okay. So we said cosine of 90 was 0. Sine of 90 is 1. So 3 times 0 is 3. 3 times I is the 3i. So far, I have one answer. I have two answers. I'm going to have two more answers, y'all, because remember, we're going to have to do this when k equals 0, when k equals 1, when k equals 2, and when k equals 3. Okay? So now, look, let's do this when k is equal to 2. So W2 is going to be 3 times the cosine of, remember, this value right here, y'all, is my k. So now k is equal to 2. What's 90 times 2? 180. Very good. So now I'm going to pull up my chart again. I'm going to go to 180. Cosine of 180 is negative 1. Sine of 180 is 0. Okay, so when I multiply 3 times negative 1, that gives me negative 3. 3 times 0i, still 0. I don't need to write it. And we got one more to do, y'all, when k is equal to 3. Okay? When k is equal to 3, look what we're going to do. What's 90 times 3? Anyone know? Very good, 270. Now I'm going to pull up my chart one more time. Here we are at 270. Remember, the cosine is right here. So the cosine at 270 is 0, and the sine at 270 is negative 1. So I'm going to say cosine here, this is 0, and then this is negative I now, because it's negative 1 times I, it gives me negative I. So 3 times 0 is still 0, but 3 times negative I, negative 3i. So when we found the fourth roots of 81, look at the answers that we came up with. We came up with 3 and negative 3, and we came up with 3i and negative 3i. All four of them. Yeah, all four of them. Alrighty, so look, y'all, we got one more to do here. We're going to look for the cube roots of 81 cosine of 204 plus I sine of 204. This one, we're going to write the results in polar form, so we can leave it in that CIS form. Okay, so look, first thing I'm going to do here, y'all, I'm going to write my problem S or Z equals 8 cosine of 204 plus I sine 204. And we're looking for the cube roots. Okay, so first thing, y'all, what I'm going to do is I'm going to just copy this formula down so that I can use it in my problem. Okay, so WK equals the nth root of R. Let me just make sure I got everything there. Yep, we're good. Okay, So remember what we're looking at here, y'all. We're looking at the cube roots. So my n is equal to 3. It's theta, sorry. So because we're looking at the cube root, this is telling me n is equal to 3. And so when we're doing this, we're going to have 3 answers, y'all. One when k equals 0, one when k equals 1, and one when k equals 2. It's always going to be, the number that you're going to end up with here is always going to be 1 less than this one here. Okay. So let's see if we can figure this thing out. We're going to go WK equals, we're taking, or yeah, we'll leave it like this. WK equals the cubic root of R, which in our case is 8, times the cosine of theta. Theta in our case was 204, plus 360k, my n is still 3, plus I sine of 204, and my n again is still 3. Okay. So look, y'all, I'm going to actually write this one like using kind of like a formula. So first question, anybody remember what's the cubic root of 8? 2. Okay. Look, y'all, when we have this cosine here, see how everything is being divided by 3? We can take each of these individuals and divide them by 3. So what does that mean? That means I can take my calculator and say, okay, look, what's 204 divided by 3? 68. Okay, so this is going to be 68 plus 360 divided by 3, I already know is 120. Okay. So far, am I good? Because it's the cube root. Right here, Jennifer, it tells me it's the cube root, so that's telling me it's going to be my n. So in the one before, it was the 4th root, so we knew our n was 4. Okay. So look, y'all, all we're going to do now, we're going to do this 3 times. Once when k equals 0, once when k equals 1, and once when k equals 2. So look, first thing we're going to do, now k is equal to 0. 2. Cosine of 68 plus 120 times 0 plus I sine 68, 120 times 0 again. Okay. Everybody agree 120 times 0 is still 0? So those are going to go away. Wouldn't this just be 2? And I'm going to use the abbreviation here, CIS 68 degrees. Okay. All right. Now we're going to do this, y'all, when k equals 1. So when k equals 1, we're going to go 2 cosine of 68 plus 120 times 1 plus I sine 68, 120 times 1 okay. Cosine of 120 times 1 is still 120. What's 120 plus 68? Okay. So we wanted to, we could write it going like this. 2 CIS 188, right? All right, and we got to do this one more time, y'all, when k is equal to 2. So W2 is going to be equal to 2 cosine of 68 plus 120 times 2 plus I sine of 68 plus 120 times p. Let's see, this is the cosine. 120 times 2 is 240, plus 68 is 308. So this is going to be cosine of 308 plus I sine of 308. And so we might just write it like this, using the little abbreviation, W equals 2 CIS of 308. There's one answer, there's two answers, and there's the third one. So that's it. And that right there, y'all, is 7.3. So let me stop recording this part here. Here we go. Oh yeah, go ahead. And let me stop recording that.